Welcome to the problem section for arc length and area of a sector. I'm going to do a number of problems. The first one says, the minute hand of a clock is 1.2 centimeters long. How far does the tip of the minute hand travel in 40 minutes? So if this is the minute hand here at 1.2 centimeters, and then 40 minutes later, of course, the minute hand ends up down here. And forgive my kind of crude drawing here of the time that has expired. In any case, the way to determine this is simply to multiply the two, but first we have to figure out what is 40 minutes in radians. Looks like it's 2/3 of a full circle, so it's 2/3 of 2 pi or 4 pi over 3. So we have here 4 pi over 3. And then the arc length is 4 pi thirds radians times 1.2 centimeters. And I'm going to do that on the side. So 4 pi over 3 times 1.2, I come up with 5.03 centimeters rounded. Okay, next problem, which says, arc length. The space shuttle 200 miles above the Earth is orbiting the Earth once every 6 hours. That's where I have to pause. I don't know why math author made such an easy mistake here. I mean, the author is doing a really good job, but I don't know why there's a mistake here. I also teach astronomy, and then it's just not true. At an altitude of 200 miles above the Earth's surface, the space shuttle is orbiting at 1.5 hours for each orbit, so for each 2 pi's. I just know that as an astronomy instructor, and you can easily find that information on the internet. In any case, let me go ahead. How far does the shuttle travel in 1 hour? Give your answer as both an exact value and approximation to 3 significant figures. In order to stay in accordance with the book, let's just do the following. Instead of using 1 hour for the travel time, let's just use a quarter of that as well, just like I corrected the 6 hours to 1.5 hours, so we come up with 0.25 hours. 0.25 hours is 1/6 of the total period. As you see, 0.25 divided by 1.5 is 1/6. That means that the angle is 2 pi divided by 6, which means we're going to have pi over 3 radians. The arc length is then going to be pi over 3 radians times the radius. The radius is not the 200 miles altitude, but the 200 miles plus the radius of the Earth, so it's 4,200 miles. And again, it says to find an exact value. Well, the exact value then would be 1,400 times pi. Miles, that is. Oops. Miles. Or when we calculate that out on the side, 1,400 miles times pi, we come up with 4,400 miles. You will see that the answer is the same in the book. That's simply because I changed 2 numbers in our problem here to 1.5 hours, as well as the travel time of 0.25 hours or 15 minutes, and that keeps the answer to be the same. That's quite fast. In 15 minutes, 4,400 miles. Yeah, those things are fast. Okay, next exercise. It says diameter of the moon. From the Earth, the moon subtends an angle of approximately 0.5 degrees. If the distance to the moon is approximately 240,000 miles, find an approximation for the diameter of the moon accurate to the nearest 100 miles. So we would have to see at how the arc length is defined, because we have been doing this all along. So arc length is theta times r. In this case, distance, let's see, ooh, look what I did. This one here is actually r, not s. I think I made the same mistake on the next one. And then d, the diameter, is the same as the arc length. And so we just multiply the two numbers with each other. First of all, before I actually do that, I have to convert 0.5 degrees to radians. So on the side, I'm going to do 0.5 divided by 180 times pi, and in radians we come up with 0.0087. And I'm just going to keep all the other decimals on the calculator, and now we're going to calculate as follows. 0.0087 times 240,000 miles times 240,000 miles, and I come up with 2,094 miles, and that should be rounded to the nearest 100 miles, so 2,100 miles is the diameter of the moon. By the way, that picture that you see here looks like there is no moon there, but actually that's what you're looking at. The black spot here, this is during solar eclipse. The sun is right behind it, and what's obscuring it is the moon. And because the light source is on the other side of the moon, that's why we only see the dark. In this case, yeah, the dark side of the moon. I didn't have a personal good photo of the moon, so I chose the solar eclipse as my photo. Okay, diameter of the sun says the distance of the sun is approximately 93 million miles, and from the Earth the sun subtends an angle of approximately 0.5 degrees. Oh, same angle as that of the moon. Just to say that's coincidence, but that makes for nice eclipses. So actually we have the same radians here. Let's see. And then it continues pretty much on in the same way. Estimate the diameter of the sun to the nearest 10,000 miles. So we're going to take the 0.0087 radians and multiply with the distance to the sun. And I might want to put in here the diameter is the arc length, roughly, pretty close to, and multiply that by 93 million miles on the side, and I come up with 811,578 miles, 811,578, and rounded to the nearest 10,000, I come up with 810,000 miles. A huge sun, of course. And all the exercises here, I keep forgetting to underline the result, but oh well, you'll find it yourself. Okay, next exercise, which says find the radius of the circle where theta equals 6, s equals 3. So r comes out to the arc length divided by theta. So it's going to be 3 feet divided by 6, which of course comes out to 0.5 feet. And the next exercise, 2 feet divided by 1 radian, and then of course comes out to 2 feet. Find the area of the sector formed by this angle here in a circle of radius r if theta equals 2 and r equals 3 centimeters. So here we would put 1/2 times, let's see if I can, there we go, times 2 radians times 3 centimeters squared. There we go. And again, I'll do it on the side. Well, I can do this in my hand. It's going to be 9 square centimeters, right? Because the 1/2 cancels the 2. And the other one is going to be 1/2 times 3 times 2 centimeters squared. And let's see, that comes out to, oops, that comes out to 6, when you plug in the numbers in, 6 square centimeters. So relatively straightforward. Okay. And the last exercise says, the moon and the sun are at first sight about equal in size. I showed you that with the solar eclipse photo a while ago. How can you explain this apparent similarity in size even though the diameter of the sun is about 400 times greater than the diameter of the moon? Let's look at the diameters. The diameter of the sun is 810,000 miles. Oh, whoops, one moment. I meant to have this one written down. So diameter of the sun, diameter of the moon. Diameter of the sun is 810,000 miles. Well, we've determined earlier that the diameter of the moon is 210,000 miles, which, as you can see, is about 400 times as large. Well, let's look at the distance. The distance from the Earth to the Sun is 93 million miles. The distance from the Earth to the Moon is, we had that earlier, 240,000 miles. And if you determined theta, you would come up with the diameter divided by the radius, and we had that earlier. That was the 0.0087 radians, or earlier given as 0.5 degrees for both of them. Or, in other words, as the diameter of the sun is 400 times larger than that of the moon, its distance is also virtually 400 times larger than that of the moon. If you take 240,000 multiplied by 4, that's 960,000 multiplied by 100, that's 96 million. So both the distance and the diameter ratios are 400 times. So a sun that is 400 times larger than the moon, remove it 400 times further, you come up with that they appear to be of the same size in radians and degrees, and that's what you saw from my eclipse photo. So that's the answer to that. The sun is also about 400 times farther than the moon. And with that, I conclude this problem section for arc length and area of a sector.